Hi everyone, in this recording we'll continue studying uncertainty visualization. So in the last notes I mentioned that frequency framing tends to be more effective than just reporting error bars. But error bars do have their place. We'll see some examples of them in this recording, as well as some variations on error bars that tend to be a little bit more evocative. So, the first situation. If you have many items where you want to communicate uncertainty in each of them, then it is helpful to have an error bar. So what I'm showing here, I have some hypothetical means and standard deviations for some data, and I want to show the mean and standard deviation for each one of them. So this is a 95% confidence interval. The idea, you could have stacked many of these kind of mean and standard deviations, and you could still read what are the ones which are the most variable, which are the ones with the highest means. All these queries are very easy with this kind of visualization. Now, since they're kind of so concise, you can actually very easily put them into other visualizations, right? So if I wanted to have a scatter plot where I show some sort of uncertainty in where the points are, you could very easily just have kind of a mix error bar and scatter plot. Right? So it's like a composed type of visualization. Right. Now, one issue, maybe kind of the biggest issue with error bars is that their meaning is not context independent, right? You need to say what is the confidence level. If you showed only a 66% level, then it looks like a very narrow bar. But then, if someone had seen that error bar and interpreted it as a 95% confidence interval, they would be very misled. They'd be thinking that your accuracy or your estimation accuracy is much higher than it actually is. Right? Your uncertainty is much higher than this. Right. So, what are some variations that can show a little bit more, right? First, you can consider using something called a point interval plot, right? Point interval is kind of like an error bar, but then you show at many levels, right? You still need to specify what the confidence levels are, right? But then you get a sense of, okay, if I want just a 66% or 90% or 99%, you can show each kind of as a graded error bar. This is done in the ggdist package using this point interval. If you use the .width command, you can control the gradation. So by default it's 66 and 95. I could give .width 66, 95, and 99, and then it would have kind of gradation and little drop-offs at each of those widths. And this is actually all the same data that I was showing up here, but you tend to see a little bit more information this way. Okay, so you can combine graded error bars with other kinds of plot, right? So something where you combine a graded error bar with the actual density is called a half-eye plot. Right? It looks like an eye, right? So these are the point intervals from above, and I'm also showing the density, right? And just like in the frequency framing recording, it's helpful to think about the densities as kind of little hypothetical outcomes. So instead of using a half-eye, you can use this dots interval, and it will show both the point interval and some dots around it. You can imagine this being very useful in different kinds of probability modeling, right? If you, for example, had a Bayesian model and you had posterior distributions for a whole bunch of parameters, it's very natural to want to show those posteriors as this kind of dot interval plot. Okay. Kind of a related idea is to show this sort of gradation via the color of the slab, right? So just like in the point interval, you want to be able to communicate gradations of uncertainty. So you show kind of the area. If you had just like a very small interval, like a very low confidence interval, you could have a darker color. If you want to have a wider, kind of more honest about like capturing all the potential kinds of outcomes, you can have this lighter color near the end. Right? It's just extending the point interval gradation idea to the color of the density. Okay, so there are a few other kinds of encodings. So here I'm showing stat interval and gradient interval. again, all the same data. So this, again, is very, very compact. You can kind of tell the difference in the levels by the difference in color here, but it tends to be a little bit harder than when you have position from the density. Here's another way of looking at point intervals where you also have some background. It kind of gives some intuition about kind of like the fuzziness of the estimation, but it's not quite as common. Okay, there is a kind of way of showing these point intervals that, according to research studies, they found that this tends to be, for non-technical audience, actually the most effective for judging uncertainty, but it's also one of the least common. So it takes a little bit of training and you have to explain how to read the plot. But this is called a CCDF, like a complementary CDF. And it's just exactly that, right? It's, you are pretty sure that the mean is going to be lying below anywhere where there's this kind of shaded gray area. And you're not so sure out here, like it might actually be in this range. And you're very sure that the mean is below this. Like if it's already dropped off here, then you're sure the mean goes below there. Right? And kind of the slopes is telling you kind of how uncertain is this estimate. So by combining the point interval with this kind of CDF type information, you get two ways of assessing uncertainty, and somehow that helps. Okay, so in all these examples, I've just been using a hypothetical normal distribution. I'm using the distributional package to make up the density for some normal. But everything I'm showing actually works just on real data too. Right, so here I've simulated some data set, not just like true mean and true standard deviation. And I'm using the same functions from before, like a point interval, half-I, everything I showed before will still apply. And here you get, it's not just like a perfectly symmetric kind of distribution. I have some empirical densities here, but the code still works.